Hi, my name's Darren McClernand. We're going to go through 8 great reasons why you should design with modulation. The first is that modulation, and specifically error vector magnitude, is an important part of almost all wireless design and design verifications. The product specs, everything you do is meant to convey signals, and modulation is part of that. What makes modulation different from S parameters or even 1 or 2 tone harmonic balance is that EVM encapsulates both the device performance as well as the signals passing through it. So the choice of EVM is actually a signal choice as well. That signal choice comes from your customer's environment. So you're actually inviting your customer into your design process whenever you choose to measure an EVM as part of the design process. In fact, it's hard to imagine not validating EVM as part of the design process, and it's never been easier or more accurate with some of Keysight's latest advancements. So although EVM is part of data sheets and standards docs, it turns out that there's lots of things that can make EVM go bad. And some of them are power dependence and nonlinearity, non-monotonicity, frequency ripple across a bandwidth, memory effects. It turns out that really strong wideband signals with high peak to average ratios are very, very stressful on a design. And the wider the bandwidth, the more stressful it is. They become very noise-like and signal dependent. And if you look at how these interdepend, there are lots of ways to do one of these parameters, but it's very difficult to take all of them into account. And that's where Keysight can really help. Keysight provides 8 distinct things that we think move your ability to do modulation as part of design rather than an end verification forward. And we're going to go through each of these very briefly and outline how Keysight is making you more successful. The first one is the reuse of standards IP in both design and test and measurement. So when you measure an EVM, getting the same settings, the same waveforms, a lot of the same assumptions in both places just takes away a whole series of questions that tangle, unraveling why you're getting a different result in both places. Is it a bad model? Is it a bad design? Is it just a wrong assumption about a filtering or a sample rate? And so the consistent approach, instead of having your best people spend precious design time, going through all these settings, you can have them just generating more value by using a consistent set of IP. And you do this in ADS through virtual test benches and through waveforms that you can leverage as waveform files and with Python. In system view or pathwave system design, you can also work with not only its own libraries, but also with the 89600 VSA and direct connection to equipment. What this does is very interesting. If you look at the system level of EDA, you do a couple of things. One is you pull some of these measurement assets forward into the design space. You also can provide, through System View, virtual test benches for ADS and Golden Gate that allow you to use these things inside those environments without actually having to relearn a whole bunch of softwares. And so by having a consistent approach across all of the design workflow from R&D through validation and into early production, you can streamline your flow, create a workflow, and actually begin the digital transformation of your company such that you can shift left. You can interoperate some of the results and models from both sides of test and measurement and design in one workflow. And that's really important for how the future will work in the coming years on digital transformation and shifting left. The second great idea is compact test signals. It's one thing to have a 5G waveform of a couple of milliseconds duration. It's another thing to have an analysis result for 500,000 or 1,000,000 time points. It's going to take a while. And so with today's wideband signals, Keysight has come up with an intelligent way to do signal compaction. And this comes from the PNAX vector network analyzer team within Keysight. You can look at a waveform and pick out a subset that from an RF analog perspective has the right amplitudes statistics. It has the right frequency response and tilt and frequency characteristics. You exercise your RF hardware with something that's statistically relevant, and you make sure that you sample it long enough that you actually get statistically meaningful effects, but you do it in a fraction of the number of points. And so this technique allows you to stress a design. It's actually built into Circuit Envelope as a simulator option. It's something that's done to the waveform. It's really not an approximation to the analysis, and so the analysis is the full accuracy of the analysis. The key is, can you get the same answer in a fewer number of points? No, in a similar vein, idea number 3 from Keysight is the idea of modulation distortion or distortion EVM, which is a faster, a little bit more direct calculation of EVM. Again, this is test and measurement IP that's pioneered by the vector network analyzer team. And what it allows you to do is decompose a composite result into just the linear portion and the distortion portion. They've done it in measurement to achieve certain effects with dynamic range, the noise floor, and getting very high quality measurements. What they do is they chop this into a repeating waveform and step a narrowband IF across it, dropping the noise floor and synthetically stitching a wide bandwidth. So they have an incentive to use as few number of points as possible. Turns out in the time domain, in transient envelope mode in ADS, you also have an incentive to use the fewest number of points. And what's interesting is if you take the EVM, the actual error signal, and FFT it, by Parsifal's theorem, you can represent that same energy in both domains. And by reducing the number of points in one domain, you can actually do that in the other domain as well. There's a way to get the EVM more directly estimated, which has been demonstrated in measurements against the traditional time domain method with the vector signal generators and the vector signal analyzers, the UXA and VXG, for example. In this plot, you see that the measurement folks have gotten lower noise floor and a higher dynamic range, and they can tell duct behaviors to a much lower level. In EDA, it turns out that there's a similar benefit. You can do it in a time domain method or in this distortion EVM method. And it turns out to be quite a bit faster in design, such that you can actually do it without directly in ADS as a post-processing step without having to have a virtual test bench or formal demodulation. That speed up allows you to do things like contour plots, and to do, in the time it took to do one EVM, you can do many. So now you can do a sweep of power, a parametric scan, or even load pull. So it makes these features make envelope capable of doing quite a bit of modulation analysis at the point of design rather than leaving it to the very end as a verification step. Idea number 4 is convolution. A lot of analysis engines use a polynomial approximation to help estimate the effects of frequency response in the time domain. And so here's an example of a bulk acoustic wave filter that is a bandpass filter, and it takes a while to settle. With one approximation, you see that it continues to oscillate and it settles to an incorrect value or a slight offset. And with convolution, we've streamlined this so that it's transparent to the user. It's literally a convolution setting in the analysis, but at the envelope level, it's finding robust answers that are important for frequency domain kinds of characteristics like EM simulations, packaging, filters, and additional external components. It's really important to be able to take these physical design attributes and bring them accurately into the time domain. Another idea number 5 is the idea of fast circuit envelope equivalence. Instead of 1,000 transistor or some large analysis that possibly has EM and a number of other things, there are cases where you can approximate that by pre-calculating a surface and then quickly just analyzing against that surface. Now the thing that Keysight brings to the party here is that these models take into account power dependence, frequency response across the bandwidth, and even transient behavior at the envelope level and memory effects. And so by solving this surface up front and then using the surface, you can show a modulation equivalent that is 10 to 100 times faster than it would have been, and for large classes of circuits, this is a very reasonable approach. Again, all these speedups really have a dramatic effect on how the tools are used. Instead of just doing one analysis that you do all your design and then as a very last sign-off, you do one analysis at the end. These speedups bring accuracy and rigor into the design process at a place where you can do sweeps, you can do optimization and look at parameter scans. So this is from an example in a workshop, a PA mimic workshop for ADS. You check the box that say enable fast circuit envelope to do these things. And in this particular 5G NR signal, here was 10,000 time points. It's a portion of a subframe. And just using this behavioral modeling equivalent gives you 3 to 10 times a speed up with very little change in the EVM, as well as ACLR and power and gain and so forth. Even when overdriven into saturation, it still shows a speed up. If you combine it with the signal compaction, you can actually stack some of these speed ups and get things that are fast enough to bring into the design process. Instead of just doing a harmonic balance point or sweep, you can actually bring in an EVM and look at efficiency in the face of an EVM, an ACLR as well, and bring these modulated characteristics right into design. Setting up some of these waveforms is actually fairly involved if you do it manually. And so if you're currently exporting a manual from a model from your environment out to a file and then bringing it into MATLAB or some other kind of simulation that's error prone. It's reversion dependent. It doesn't necessarily carry all of the physical effects. When you bring the system environment into ADS or Virtuoso, you never have to leave the RF design environment. And so because you're operating this system intelligence is actively making and analyzing waveforms, you can do a closed loop. You can do it on Linux and floating licenses and use all of your current PDKs and EMs simulations and stuff. You never have to leave. And if you want to do it on full envelope, you can do that. If you want to do it on a fast circuit envelope or take some of these other approximations, you can do that too. But you have full control over the accuracy, and because you have a component that you can just drag and drop, one of these VTB components is in fact a source and a sink with parameters that are CAN. You can account for the true device without having to create intermediate behavioral models that you have to track in a file system or communicate. And it turns out that when we spoke earlier of all the things that screw up EVM, you can have rigorous 5G or Wi-Fi 7 waveforms generated or analyzed and accurately look at the effects of modulation on your circuit. And in fact, since you can close the loop on this, you can actually do digital pre-distortion. And what's interesting is that you can look at bias and load pole, package resonances and EM effects, even a little bit of thermal. Anything that can be swept can be done with one of these virtual test benches. Now with DPD specifically, you're taking a closed loop approach and actively using that signal processing to, it's like augmented reality. You take that amplifier and wrap this virtual environment and you can see what your customer does. Because really, if you're a PA designer, you don't know what signals or what linearization algorithms your customer is going to use. Sometimes they tell you, sometimes they don't. But if you can linearize your amplifier at the point of design, you can actually make your amplifier easier to linearize, or make sure that it covers the bias and bandwidth and has the flatness that you need that to make it correctable. How correctable is my amplifier? You can see ahead, and it's kind of like augmented reality. Are you going to use the DPD coefficients that come out of the design process really in real life? It's unlikely. Because everyone who does digital pre-distortion does it slightly different. That's part of their special sauce. But what happens is you as a PA designer can see what they're going to see. Here's what my amplifier is capable of up to this power, up to this, under these kinds of signal conditions of carrier aggregation or peak to average ratio. And I can gauge things like efficiency under certain conditions and tell my customer, even demo to my customer what this product is going to be capable of when it ships. The final DPD is sort of the culmination of a bunch of things that have to work. All of these acceleration techniques and accuracy techniques and waveforms and all those things have to work for DPD to be active. If you do all these sweeps and analyses, you end up with a ton of data because these are modulated waveforms. There's a lot of data walking around. How do you deal with that data? Increasingly, companies are using Python. Python has the advantage of it's free and it's everywhere. The skills are plentiful. And once you can connect ADS's data into a data lake of a company and automate some of these data manipulations, or even instrument access with Python, you can plot and automate and connect your data stories within your engineering environment into a workflow that isn't just one button push, but is persistent, that it can stay connected and actually be run headless by some other invoking system. So it's one thing to have a system that is driven from the user interface by a skilled human. It's quite another to have the automation hooks to be able to take a program, an invoking program, say a requirements or model-based system engineering program, to invoke these simulations and run these analyses, harvest these results, and get them back someplace. That is increasingly important. And this is somewhat unique still to Keysight in the RF EDA arena, to be able to not keep the data locked in a walled garden where you have to pay some license to be able to program it or manipulate it, but to be able to take that data and use it elsewhere in your enterprise for debugging, for forensics, for troubleshooting, or even for exchange with partners and clients. These models and these stories are increasingly important, and Keysight is actively investing in these stories. So to summarize, Keysight provides, just we have 8 here, but there's a number of forward-looking techniques that give you the right result. And then once you get the accurate right result for both the DUT and the waveform, now how fast can we go and how can we move that data around effectively? Really, Keysight is investing in the direction that your company needs to go. Thanks very much. This has been Darren McLaren for Keysight, Pathway EDA.